I want to turn it over to Barry, who I've known for a long time. Very excited to hear talk about this reflection stuff, which he's had a large hand in helping get across the finish line. Evan knows it's been in the committee for half of forever to begin with, so it's pretty exciting to see something actually making it to C++ coming out in 26. With that, take it away, Barry, and it's all yours.
All right, hey everyone. Yeah, so excited to be here. Talk about reflection. So like Rob said, C++26 is going to have static reflection in it, and it's a pretty big game changer for what's possible in the language. But there's a kind of a lot to talk about, a lot to learn, kind of understand the shape of it. So what I was hoping to do today is I'm going to start with just kind of a high level tutorial of what the shape of reflection looks like. But given that it's going to be kind of hard to look ahead and say like, okay, well, what's the point of this? And so I'm going to walk through implementing a particular use case, which is implementing a structive arrays vector type automatically for any aggregate. And kind of in the process of doing that, you'll kind of see a lot of techniques for how to do things, what sort of thing is possible. And also along the way, I'll go on a lot of digressions for how to do different kinds of things differently, just to kind of give people a sense of what's possible, what do different techniques look like, so you can kind of gain some familiarity, some exposure to this, right? Like I don't necessarily expect everyone to immediately become experts in reflection over the course of watching this talks, but you maybe you watch this one, you watch another one, and over a while you start to build some intuition about it. So we're going to do everything today on Compiler Explorer. Hopefully I can share the correct window, which is this. Everyone see this just blank Compiler Explorer window? So that's where we're going to work with today. So to start with, there's two implementations of reflection that are available in Compiler Explorer right now. There's the Clang Bloomberg fork that was implemented by Dan Katz, and there's the GCC trunk implementation, which is from Marek and Jakob. The GCC one is more accurate to the spec, um, but it turns out that there are some wording issues that they've discovered along the way. So it has some things that look like bugs, and so I'm more familiar with the limitations of the Clang one, so I'm going to use that one for now. And I'll talk about kind of what C++26 will actually look like versus what Clang actually implements. All right, so to start with, reflection introduces two operators. A reflection operator, which takes any source construct and puts it into the reflection domain. So for instance, uh, we can reflect on a type, we can reflect on a namespace, we can reflect on a class template, we can reflect on a class template specialization. If I have a type here, I can reflect on a non-static data member. If Importantly, if a non-static data member happens to be, let's say, a bit field, I can reflect on a bit field. And so all of these things work. So you'll see also that all of these things have type stood meta info. Reflection is a monotype design. I'm gonna actually go ahead and remove the unused warnings. Reflection is a monotype design. Taking the reflection of anything gives you an object of type stood meta info. This is a new scalar type in C++26. And it's kind of interesting that we ended up with a design where the reflection of anything is just a meta info, right? Um, there are other potential design options, like maybe the reflection of a type gives you an object called type, the reflection of a namespace gives you an object called namespace, something like that. And it turns out that the monotype design has a lot of interesting benefits. It makes it, for instance, obvious how to store heterogeneous collections, and it turns out to be easier to manipulate a lot of ways. So we'll kind of see what that ends up looking like. Um, so this is kind of the way we get into the reflection domain. And then reflection is designed so that you kind of get into the reflection domain, you do all your work in there, and then eventually you get out of the reflection domain. And the way you get out of the reflection domain is with the inverse operation of reflection, which is splice. So if I have a reflection representing a type, then if I splice that reflection, I get back a type. So the splice R1 was a reflection representing the type int. So if I splice it, which is this syntax right here, I get back an int. If it was a namespace, then I get back a namespace. If it was a template, then I get back a template, and then I can instantiate it, for instance, with a different type, right? So all of these things kind of work, right? Um, in the other thing that you can do with reflections is, of course, we have a very large library API of things that you can do. At its basic, we can just query things like, is this thing a type? Is this thing a non-static data member? And you can see that these things return true. But of course, there's all sorts of interesting transformations, type traits, and whatever. So at a high level, this is kind of the general shape.
We do have
The
a
other,
question. If you
what?
we do have a question. I was just gonna bump in there.
Sure. Let me kind of keep going for a second, then I'll stop it. The other thing to keep in mind with reflections is that reflection is a compile time facility. The reflections have no meaning at runtime, and so one of the things we do is that we enforce that these things do not persist into runtime. So if I try to declare R6, for instance, as just a regular object, that's not possible. You see that there's a compiler here that the variable is of const only type. This is a new property that we ascribe to types that if they have a meta info somewhere in them, including pointers or references somewhere in them recursively, that thing cannot persist to runtime. And so this is one of the reasons that we also have const eval functions, is to ensure that all of the reflection operations don't lead to cogen. All of this stays in the compile time domain. Some of these things might change eventually, but for now, that's kind of the design, and this is enforced. So every operation with reflections has to stay at compile time. So you have to have context for objects. You have to use const eval functions. Yeah. Okay. What's the question?
Yes. Can you actually, do you have to have the STD meta info um, there, or can you just use auto and have the type inferred?
Yeah. You can just use auto. That's fine. I was just making it clear that this is always the type. Okay, so this is kind of the high level, right? So we have a reflection operator to get us into the reflection domain. We have a splice operator to get us out of the reflection domain. And then we have a whole bunch of functions, like hundreds of functions that let us do things while we're in the domain. So importantly, also, one of the things that I find that people will get wrong, and will really struggle with, is the idea that when we splice a thing, this splice operator, the argument, the expression that we're splicing has to be constant. And so if I have a function, apparently my C key is broken, that takes a std meta info parameter and does something with it, I cannot splice it in here, right? If I try to do if R is supposed to represent a type and I try to splice it, like I can't splice it in here because R is not a constant, right? Function parameters are not constant. You can't do things like this. And so we'll go through also over the course of this, we'll go through a few examples where it seems like this limitation means that I can't do anything, and we'll show kind of how you can actually solve this problem anyway. But one of the things to keep in mind, and like I think the way that I find it useful to think about this, is that a constant function is just a function. It's a kind of function that has this additional restriction that it can never lead to runtime, but it's still just a function. And just because it happens to only be run at compile time, that doesn't give it special powers or changes the meaning of how parameters work. Okay, so the example that we're going to go through today, I'm going to kind of delete all this now, is a structive array vector, right? And so we want to implement a type. I'm just going to call it SOA. And it's going to behave like a vector to the extent that's possible, except instead of having its storage be contiguous T's, it's going to store all the members of T separately in separate arrays. This is a common technique in a lot of domains to use memory more efficiently, to pack things tighter, to have better cache locality for things you might want to access. I'm not going to really talk about like why this is useful or valuable or different interesting things about it specifically. There's other talks that are better for that. We're just going to talk about how to actually implement it. And so before we even talk about how to actually implement this thing, let's talk about the constraints, right? Because we can't have a structured array vector for any type at all, right? Like you can't have an SOA vector of string because, okay, if I pull apart all the members of it, then I destroy the string. That's going to deallocate the memory. So like having the members around isn't very useful. So it turns out there's kind of like three properties that I need in order to be able to do a SOA vector, right? I need to be able to destructure the T into all of its components, and those components really have to be independent so that the T's destructor doesn't invalidate them. I also need to be able to restructure the T because eventually you're going to put T's into this thing and you want to get T's out. And if all I have are the components, I need to be able to put it back together. And I also need to be able to name the storage somehow, right? So however I'm going to store it, I'm going to assign names to it. And part of that reason is to have user-friendly API that I'll talk about later. And so these are kind of the restrictions. And if you think about it, like these two together kind of combine into T as an aggregate. And this one is basically T has no base classes, right? That's kind of our restriction that we want to implement. And so we can do that as like a normal concept, and we can start out and right, like just can SOA or something. And we have a type trait for aggregate, right? Is aggregate B. That's a C++11 thing. And in order to check if it has base classes, what we can do is we can now using reflection, we can ask for all the base classes and check that there aren't any. So the basis of API is kind of a mouthful. So all the members of APIs take this access context thing. And this was kind of a choice to handle how you handle exposing private information. In this case, I don't care if your bases are public or private. I just need to make sure there aren't any. But it is kind of a mouthful. And so the thing that I'm going to do kind of for the purposes of this talk is I'm just going to have just a global unchecked for this just because it's a little bit easier to type. Okay, so this is one way that I can implement CanSOA. But it's probably not the most interesting way. And what I really want to show is that when you start using reflection, you don't really have to write everything as a template all the time. Up until now, every time you do any kind of type traits, metaprogramming stuff, everything has to be a template, variable template, function template, whatever. But in reflection land, we kind of think about things more as being functions. So I want to write this more as a simple Boolean predicate. So I'll call it CanSOA with a reflection representing the type that returns bool. And so this part of the predicate is going to look the same. Obviously, I already have the type. But how do I do the is aggregate part? For this particular case, well, for every type trait that's in the standard library, we provided a const-eval function equivalent of them that has kind of the same shape. So we can implement it this way. So importantly, this is just a regular function, right? It's a function that takes a reflection representing type, returns bool, and it has the same properties. Where is aggregate type is now the const-eval equivalent of the type trait that we already have. So you might have noticed at this point that I'm calling these functions unqualified, right? Is aggregate type and basis of. This is because we added a special rule that for std meta info specifically, it has std meta as an associated namespace. So this is actually doing ADL, and this means the same thing as qualifying all this out. But if you qualify all this out, it tends to be very verbose, which is why we added this rule to begin with. This makes it a little bit easier to read. Okay, so you might wonder that like, okay, that's cool and all that the standard library provides a dedicated function for all these traits. But we have our own type traits in our own code base. Like, how do we do that? Because one of the things I can't do, as I pointed out earlier, is I cannot write this. Right? If I have this as a variable template, I can't just use the variable template because I cannot splice type here because type is not a constant expression, right? And you can see that in the compiler, right? Splice operand must be a constant. So if all you have is your variable template, how do you do this? And fear not, like there's a solution for this too. And it's pretty interesting, and I think it's sneakily one of the most useful functions in the entire reflection library. And that function is called substitute. What we're going to do is we're going to substitute into this template with this argument. And what this means is substitute takes a reflection representing a template. So in this case, its aggregate V is a variable template, but it doesn't matter what kind of template it is. And it takes a bunch of arguments. So this is equivalent to writing this expression, right? This gives me a reflection representing that result. But I can't write that expression, but the compiler can give it to me. And the reason that the compiler can give it to me is that it has type info still. So we're not kind of violating any of the properties of how functions behave. This is still an info. But what's interesting about it is that it's an info that I know something about, right? Specifically, I know that is aggregate v is a variable template of type bool. So I know that R is going to end up representing a variable of type bool. And I can get that result out using a different function called extract. So I can write it like this. So kind of to test that this works, so I'm going to add a struct point. I'm going to call it square actually, which will be the type that we'll use for the purposes of this talk. And I can verify that I can indeed SOA it square. And you'll see that this will compile and work. So the substitute extract ends is very interesting. And I think kind of the closest analog to this is something like stood any. A reflection can represent anything, and you don't really have a lot of information about what it actually represents, but if you know what's in there, you can use anycast to pull the value out. And if you get the value wrong, then the anycast is going to fail. And that's the same here. So if I try to extract this as an int instead of bool, this is going to fail because it's not a reflection representing int. And in particular, like the compiler error here is actually pretty nice, right? You can see that the reflected value of const bool cannot be extracted as a value of type int. And so as long as you know what it is, you can pull it back out. And there's a lot of reflection problems that can be solved by coming up with a template that has the right shape for the problem that you need to solve, and then substituting and extracting around that. And for example, you can even wrap up this pattern into a nice way. We can call it, let's say, pred, because I'm going to take an arbitrary, sorry, a reflection representing a template, and I'm going to return a lambda that's going to take a bunch of arguments that's going to return this extract bool substitute dance. Oops. Bool args. And I can use this to wrap stood as aggregate v. And now my as aggregate is just a unary predicate around the type that works the same way, right? So this is just a convenient way to wrap this up. Okay. Anyone have any questions about that part so far?
Yeah, is it possible for extract to deduce the type?
No. Because if it was possible to deduce the type, you would basically your function would cease to like really behave as a function, right? You need to know what the type is in order to preserve kind of function properties. If your reflection is a constant, then you can just splice it and you can get the type directly. But if it's not constant, you kind of just have to know. Yep.
Yeah. Can you actually use, I mean, can you actually use some of the reflection properties at runtime if you had like a case where you needed to do have some proper or get the properties of a class that you are determining at runtime, or like for
No,
example,
reflection is purely a compile time language feature. If you want to do something at runtime, you can do something to persist whatever you want to do to runtime. But that's something that you have to do for yourself.
okay.
This isn't like Java runtime reflection or anything like that.
So basically there is the limitation that none of this will persist at runtime. Runtime, it'll always be at compile time.
Yeah, that's right. Okay. So now that we have our constraint and we're sure that we're only going to instantiate SOA vector with types that are meaningful, let's talk about the storage. Right. So for a type like square, there's a couple ways to think about the storage for what SOA vector should be, right? And the simplest way is that I just create like a std vector of char named X and a std vector of long named Y. And I could do that, and that's kind of easy. But it's also kind of boring, I think. And more importantly, like this just like isn't a very good implementation of SOA vector because if you think about these two vectors, they're always going to have the same size, they're always going to have the same capacity. So it's just like wasteful. And well, while I'm not trying to like produce like the most optimal performance ready structure here for the purpose of this talk, like I don't want to prematurely pessimize either. And I think it's more interesting to do it a little bit differently. So instead, the storage I'm going to do is I'm going to make a char for each one, or sorry, not a char, a pointer for each one, and then store the size and capacity separately. That'll probably line up more with what people actually want to do in real life. And so C++26 doesn't really have any code generation facilities. We're going to think about what to do with those later, but it does have precisely one code generation facility in it. And that facility allows you to take an incomplete type and complete it with specifically a set of non-static data members. You can't generate member functions, you can't generate constructors, you can't generate even static data members, only non-static data members. And thankfully, that's actually all you need for this particular problem, and it turns out to be all you need for a pretty wide range of other interesting problems. So it's going to be pretty useful, but just know that this limitation exists. So we start with the pattern that to learn here is you declare an incomplete type, which because our storage is going to be pointers, I'm going to very creatively name the struct pointers. We had a const eval block that is going to do some stuff and is eventually going to call define aggregate, which takes a reflection representing the type that we're completing, and then some reflections of the data members that we're going to be generating. And when we do this, when we're done with the const eval block, that type will be complete, and then we can just use this as if we kind of handwrite it. So we'll have our pointers, we'll also have our size, and we'll have our capacity. Okay, so a const eval block is another new C++26 feature. Its purpose is to basically give us a place in a declaration context to provide arbitrary expressions. And so what we want to do here is we want to iterate over all of the non-static data members of our type. And for each one, we're going to create a new data member spec for the data member we want to use, right? So note this is a regular for loop. Member in non-static data members of our type with unchecked. We can push back. So data member spec. So this API, by the way, is going to change in C++26. It's not what Clang implements right now, but for now, I'll show it this way. So data member spec is going to take the type of the member. So the type of the member is we want to take the type of the original member and add a pointer to it. And there's a type trait for that. So that's just add pointer type of the member. And then it takes a bunch of other properties, one of which is the name, which we want to preserve. So the name is going to be the identifier of the member. Pushback specs. Okay. So at this point, we can also start by checking out to see what we have here. So if I have vector, I can kind of static assert for now that the type of what do we have? V dot pointers dot x is char, and the type of v dot pointers dot y is long pointer. And this hopefully will work. Cool. And so this is also kind of messy. One of the other things that we can do is we can take advantage of the fact that a reflection is a monotype design. So we can actually start by saying like, okay, we'll start with our members like this. And we'll actually mutate them to be something different. This works too. It's probably going to be more efficient because we don't need to create a new vector, right? And so, because std meta info can represent a non-static data member as it will with the return of this function, and it can also represent something called a data member description that I'm going to get as a result of this function. So that works. I'm also going to just preemptively wrap this up because it turns out I may or may not be using this function again in the future. Um, so I'm going to kind of move this over here and change add pointer to F. And then what we're doing is define aggregate is just the transformed version of stood meta add pointer, which is a little bit nicer, I think. Note that here I do need to qualify stood meta add pointer because I'm passing it to a function, so ADL doesn't apply. But otherwise, this is the same operation, right? So here I'm mutating all the infos here. This should be probably about as efficient as you can do this. And now voila, I have my storage. Yeah, question from Ben?
Yeah, so I'm wondering about the semantics of the evaluation of these const eval blocks at declaration scope.
Mhm.
I'm guessing that it's probably evaluated like once per template instantiation, and I'm guessing that they're probably like top to bottom, like if there's multiple const eval blocks in the scope of a single class. Is that correct?
Yeah, that's right.
Okay, thank you.
Sure. There's also very tight rules here around. So when you call define aggregate, the specific type you're defining, there's very tight rules about the relationship between what type you're defining and the const eval block that this call has to appear in and what the relationship between those two things in. And that is because we wanted to tighten the rules down enough so that you couldn't use this to observe a bunch of other things about the compiler. Originally, the design was you could just call this function from anywhere and define any type with it. And people put together all sorts of wacky examples that let you do things like observe the order in which compilers try to perform overload resolution, which is, I guess, interesting, but it's not actually useful to be able to observe. And who knows what shenanigans people would come up to like depend on that order. So it's a lot better to just lock it down for now. Yeah, Michelle.
Yeah, I just was wondering. I noticed that you kept the square as a struct. Let's say that you needed to have like a class and class arguments inside of it, but um you still wanted to do the aggregate, and your data members were separate. Is there any way you can kind of do that with classes, or is it just kind of limited to uh,
Do what with classes?
well, do with classes where you have a defined predefined constructor where you take in your data members to initialize it, and then
Well, so
uh,
part of the requirement for in order to this works, I need to be able to eventually produce a square out of its members. So I need to know that I can construct the thing back. The aggregate requirement just ensures that I can do this. I mean, you could come up with a different design which allows construction to work some other way, but this is kind of the simplest thing to demonstrate.
okay, so this is only for demonstration. There could be some ways you can do it with like normal classes.
Sure.
Especially those that don't necessarily have a default constructor, but has maybe a copy constructor and a like an initialization constructor as well, or
Right. Well,
initial.
I don't need the default constructor anywhere, but yeah, I mean you could do different things.
Thank you.
Okay, so now we have the storage and we have our requirements. It's not a very useful vector if we can't put things into it. So let's go ahead and start doing that. We'll add a pushback and we'll just make it just take a t const ref here, and we're gonna start by we'll push back sorry, E4, and we'll push back, let's say C6, right? And then I want to make sure that eventually like these things actually get into the vector, and we'll check. And for now, you'll see that I've just made everything public so that I can add these additional debug things. So we'll make sure kind of at the end that I can print, let's see, the contents of the x's. So that's going to be v.pointers.x, v.size. Right. And so hopefully at the end, when we implement pushback, we'll see that we have two spans of size 2 here, where the x's are going to be EC and the y's are going to be 4, 6. You can see right now that they're both empty because obviously we haven't done anything. So pushback, same idea as any other kind of vector. So if our size is going to be equal to our capacity, we need to grow to some increased capacity. So let's say max, whatever is 5 of 2 times capacity. Um, and then and then now we definitely have enough allocation, so we'll go back and do put something in here. So we'll start with grow because of course we need to get that out of the way first. And here we'll start with kind of like our next new language feature. So right now, how does grow work? We have a bunch of pointers, and for each one, we need to allocate new space for it, copy or move all of the members into the new pointer and deallocate the old one, right? And so one of the things I'm definitely not going to worry about for this talk is like exception safety. Okay, like I allocated one block and then something through while I was copying over. Like, what do I do? Like, I don't care. Let's just pretend that that's not really like a problem here, just kind of for simplicity. So what we're going to do is because each of those things is totally independent, we're going to loop over all of our pointers and we're going to grow each one separately. And then when we're done, we're going to update our capacity. Right? So this is called an expansion statement. It's another new C++ 26 feature. And expansion statements are kind of a very useful way to have compile time loops over various structures. There's 3 forms of them, although there's only 2 of them I'm going to use in this talk. One is looping over tuples. So pointer is kind of like a tuple. This will loop over every element in that tuple. And there's a range-based version as well, which we'll show a little bit later. So this is basically iterating over for each pointer member in that pointer with pretty nice convenient syntax. Since what we're doing logically is a loop, so it's kind of nice to be able to express it as a loop. And so what we're going to do here separately, we'll call this, where's mine? Typing is hard sometimes. So in this particular case, I find it I don't actually need this to be a separate class template. I could introduce the body of this in here. I just find it nice that like the template syntax has this nice pattern matching. It's kind of nice to pull out that U right here, which is I could do it here, right? Because I could do type of pointer, which is going to give me I could do it this way as well, but I just don't want to. So what do we need to do for grow? We need an allocator. We're gonna allocate some memory of our new capacity, and this is kind of boilerplate. So I'm just gonna fly through it. We'll just like move all the elements over to the destination. Then we'll destroy all of the elements, so the old one, and then we'll deallocate the old one. And then we'll find out later if I got all the arguments in the correct order. Deallocate pointer capacity. Return destination. And hopefully, we'll kind of find out in a bit what will happen. Okay. Well, it compiles, so that's a good start. So now we have enough memory to definitely put this value somewhere. And we know that, eventually we're gonna put this member in here and then increment the size at the bottom. Right now, this will print some garbage because I haven't actually put anything in there, right? So we just have like unallocated memory. So, okay. So now the question is, how do we actually go ahead and put a new member in, right? So what I need to do is I need to take value, I need to decompose it into all of its members, and I need to put each member into each pointer differently. And so how do you do that? Now, it turns out that I could come up with lots of different ways for doing this. I don't know which one is better. There's a lot of different ways to define better, actually. And so I thought it would be more interesting if rather than kind of picking what I think is the best one right now, I'm going to show you every way I can think of solving this problem. And so you can kind of choose for yourselves which one you think is better for whatever reason. We'll kind of go through them one at a time. Okay, option one is probably the tertest way to do it. One of the other C++26 features that we have is structured bindings are allowed to have packs in them right now. So I can unpack pointers into all of its members, and I can unpack the value into all of its members, and then I can use std construct at to construct in the right spot all of the things. Okay. So for people that have done a lot of template metaprogramming, especially since C++17, C++20, C++23, this idea of folding over a comma will be pretty familiar, right? This is just the way that you do loops. Even though if you think about it, it's a very strange way to spell a loop because it's a comma. But that's kind of the way that we're used to doing things. And so you can see, by the way, in the output, so now we have the output that we expect, right? So this option worked. We have E and C in the X's, and we have X and Y, 4 and 6 in the Y's. Actually, I'm gonna add a kind of label here, make the output a little bit clearer. But this way works. All right. Now you might not like this way because it's a weird way to write a loop. And I mentioned that a different way that we can use expansion statements is I'll show in a sec. So option two is we're gonna actually start the same way. We're gonna have our members and values, but instead of folding over a comma, we're going to loop over numbers. So if I want to put over the numbers from 0 to size of pointers, and now this will look the same way. And then this. Okay. So this also demonstrates several other C++26 features. When this catches up, this should work, hopefully. Cool. Okay. So std views iota is a range, but it's a range that we can use at compile time. And one of the other interesting powers of an expansion statement is that you can declare the initializer context we're here. Right. So because we're not really looping at runtime in the kind of same way in the sense of mutating an iterator as we go, as with a regular for loop, we're stamping out instantiations. And so even though each of the elements of our views iota is a size t, we can get them as a constant here. And in particular, we need it as a constant here because we also have pack indexing right now as another new C++26 feature, right? So pointers and members are packs. And so this is a way to get the ith member of those packs. This is the syntax that we ended up. So this does the same thing as option one, except we're just looping in a different way. This was a fold expression, and this is an extension statement over indices. Yeah, Ben?
Is it possible to use something like views zip over the two packs?
Yeah, so I'm glad that you asked that question. Please hold. So is a good, you're looking ahead a little bit. So another way to do it is rather than using view zip, I'm going to do something slightly different, is that I'm going to do a tuple zip. So we'll do a tuple zip over our pointers and our value. And this is now the same thing. I have a pointer, I have each pointer and value a little bit separately. So sorry, construct at pointer plus size mem. And then so of course I have to implement tuple zip. And so let me just do that real quick. Now, so this is kind of an interesting problem if you're curious to how do you generalize what I'm about to write to a variadic. But for now, we only need the binary case, so that's a bit easier. So it's to time. So we can implement tuple zip, right, by unpacking both of our tuples into a pack and turning that into a tuple of tuples of references, right? Std_tie is a convenient shorthand for giving us a tuple of references into each thing. In this case, I don't care. I'm not preserving value category at all. This is always going to give me L value references, which is fine for this very simple example. Because that's all I want to do, right? I want to zip over these tuples. And this also works, as you can see. Right, so here's kind of option three, which is the tuple zip. Now, this is not what you actually asked. What you actually asked was view zip. And so that is going to be slightly more interesting. So let's start doing that. So now with view zip, you kind of want it to do the same thing, right? I want to use structured bindings and I want to pull out my reflections of non-static members separately. And in order to do that, I want to declare it const_expr. Now, in C++26, we do have const_expr structure bindings. You were not able to actually declare structure bindings const_expr up until now, but Clang does not implement it yet. And so we'll start with this. And because Clang doesn't implement it, this solution is going to look really ugly. But kind of pretend when you look at this, like if I could actually do this, it would look a lot better. Right. So you can see right now the error that I get is that decomposition declaration cannot be declared const_expr. That's just because Clang doesn't implement this feature yet. I think GCC does, but I'm actually not sure. But we'll do it this way. So std view zip. Now, std_view_zip takes two ranges, so we're going to write those out. It's non-static data members of, we need our pointers, and we need our members. Right, this is also accounting for us. Now, in the body here, what I'm going to have is I'm going to have a tuple of two elements in it, one of which is a reflection representing a non-static data member of the pointers, or sorry, colon, and the other of which is a reflection of non-static data members of T. And the way that I use those reflections is with a splice. So this is going to look like, now the pointer is going to be pointers.splice. So I mentioned that this looks ugly. I'm sorry. I don't know how else to do that. So pointer, this is going to get me that pointer now. And then likewise, value.splice should get one of, yeah. Right. So this is really ugly because I can't use structure bindings, and I can't use it in here either because it's a splice, so I need it to be constant. So there's just no way for me to do this in particular. Okay, what do I have? Oh, what isn't like here? Am I missing a parens or something? Okay, so now we run into this other problem. We say context of available range must be initialized by a constant expression, and then eventually here we get pointer to sub-object if heap allocated object is not a constant expression. So this is one of the unfortunate limitations that we have for C++26 right now, which is that while vector is usable during constant evaluation, you cannot have a context for variable whose type is vector that actually allocates. That's because we don't have a feature called non-transient context for allocation. Basically, you're allowed to allocate during constant evaluation, but that allocation cannot leak out of that constant evaluation, right? We don't know how to do that yet. We don't have rules for how to enforce to make sure that your program just won't blow up at runtime. And so we just completely disallow it. And this initially makes it seem like this whole thing is completely non-viable. Thankfully, we have a interesting workaround for this, which I'll talk about in a sec, which is define static array. So what define static array does, and so you can see that this compiles and works, and I have the right answer again now. So what define static array does is it takes an arbitrary range and it creates a static storage duration context for array with the contents of that range, and then it returns a span referring to it. So now it's a span, which is going to point to something, but it's pointing to something with static storage duration, and so there's no actual allocation that's going on here. So this is fine. This is comically verbose, but it works fine. In fact, I'm going to go ahead and I'm just going to preemptively write a shorthand of this that's going to just kind of, for clarity, what it's going to do is it's going to return you a span of const info. That is all of this. Let that print. Okay. And because we're going to use this function a few more times, so let's just be a little nicer about it because this is too much. All right. So this hopefully works. Except I missed a semicolon. Cool. All right. So this seems magical. And some of you might be thinking that it might actually be some magical compiler intrinsic shenanigans, but it's not. And I want to kind of demonstrate that it's not and demonstrate kind of one of the interesting things that reflection allows us to do is I'm actually going to go on a digression here and we're going to implement this right now. I'm going to kind of make it very clear that I'm implementing this right now. I'm just going to call it define static array 2 because, whatever. And this particular one, I'm just going to stick in namespace stood um, just because so I don't have to qualify everything all the time. And so what define static array does is it takes an input range, and this is range value t of r. And it's going to do two things, right? So first, we're going to do something that kind of sounds like we're cheating, is that we're going to call another function called reflect constant array. This is actually the name of the function that's in the standard library, but we're going to implement that one too. On that range. And so what reflect constant array is going to do when we actually implement it is it's going to give us a reflection representing an array of with the right contents, with the right shape, and so forth. And once I have that array, well, I know it's an array. I know what type of the what the type of the array is, and so it's easy for me to turn that into a span because I can extract the pointer from it and I can get the extent of the array this way. And so while the type of the array isn't a constant expression, I know that the type is an array type, so we have this type trait stood meta extent that gives me a size t. So this is totally fine. All right, so it's because span takes a pointer and a size, that works. And now we'll go ahead and we'll do the hard part, which actually isn't that hard either, which is reflect constant array. So now, in order to return a reflection representing an array, I need that array. So we're going to start with that. I'm going to call it the array because I'm not very good at naming, and this is good enough. All right, so here's our array, right? It's an array with some amount of values of some type. And so if you recall from earlier, one of the things I mentioned was that one of the most interesting techniques in reflection is that when you want to solve a problem, you find a way to construct a template that has the right shape of the answer, substitute into that, and extract out of it. And that is precisely what we're going to do here. Const val auto, reflect constant array 2. And this one just returns an info because we're going to return a reflection representing this thing. I don't need to anymore. So actually, in fact, I also don't need that info, right? Okay, info. So what I'm going to do is I'm going to have a vector of info representing all my arguments, and that's going to start with a reflection of this type. Ranges, range, ATT. I don't know why, sorry for the extra brace. Okay, so we're going to start with a reflection representing the type. And then what I'm going to do is I'm going to loop over every element of this range. I'm going to push back another reflection representing that element. Then I'm going to substitute into the array with these arguments. And then if I give it a sec, bam, it works. Okay, so what's going on here? One way to think about substitute is what we do is we take all the arguments that we want to pass in, and substitute is going to remove a layer of reflection. Right? So for instance, in the first example we saw earlier with is aggregate, I'm not passing in the type T, I'm passing in a reflection representing the type, and then internally we're removing a layer of reflection to get a reflection of the resulting template specialization. And that's exactly what we're doing here. We're starting with a reflection representing the type T, and then we need a reflection representing each value. So we're adding a layer of reflection here with reflect constant. Reflect constant is another reflection function that takes a value and returns a reflection representing that value. The other interesting thing about this example is you can see that this template is heterogeneous. It has one type parameter and it has a bunch of value parameters or constant template parameters. And so in template metaprogramming up until now, heterogeneous templates are very difficult to deal with, right? A lot of template metaprogramming libraries kind of ignore them entirely, right? Boost MP11, which is my favorite, it basically only supports type lists and value lists, right? Everything either has to be all types or all values, and because like we don't actually have a way of dealing with these things particularly well, and one of the advantages of the monotype design for reflection is that you can see like this is very easy to deal with. Args is a vector of info. Those infos represent different kinds of things. It has one reflection representing a type and a bunch of reflections representing values. But that just works. And so you can see that the whole implementation of defined static array was what? 20 lines of code, not even, and nothing particularly complicated. But it's kind of cool that this stuff is even possible to deal with. Of course, it is comically verbose, kind of on every side of things. So a different way to think about it, if you start going the route of dealing with reflections representing non-static data members, you probably won't want to do things a little bit differently. You'll probably want to store the pointer mems as static data members to make it kind of easier to deal with. So this is NSTMs of pointers. And we'll probably want to store the mems in the same way also. And having these as static data members kind of it makes it easier to deal with. So you can go back to looping over numbers with std iota, but in this case, it's up to members.size. And that also makes the construct out a little bit easier to deal with. So now pointers dot, this will be pointer mems of I plus size and value dot members of I, which should also work modulo typos that we'll find out in a sec. What I call it, mems. Yeah. And which of course this is much nicer to read than having to write all of this stuff. All right, so here's 5 ways that we kind of approach solving this problem. Again, whichever one you prefer, there's different benefits, especially for different kinds of problems. Yeah, Visha?
Yeah, I noticed that you use pushback, but what if you wanted to use the in place back function rather than the pushback? Is there a way, would that be something different, or would that be kind of um the same process because you're not necessarily passing in the T, you're passing in the arguments to construct T.
Okay, well, how about you think about how you would be able to solve that problem? Because it's very not different actually at all from
Uh,
this. Yeah, Dusan?
Yeah, hi. What are the compile time implications? Like, which of these compiles longer or takes up more resources?
So I don't know. And I'm also not really in a position to benchmark this stuff because the Clang fork wasn't implemented from the perspective of how do we make things compile as fast as possible. It was written from the perspective of this is an experiment to see if any of this works at all, and how do we work through different design decisions. And so a lot of it just isn't implemented from that in mind. So benchmarking the Clang one right now isn't particularly interesting. Like the numbers you get, I don't think are really going to be particularly informative. The GCC one is probably a lot more production ready, but even there, like I don't know. So I don't know um, what is I don't know what like I would my personal guess would be that this one would probably compile the fastest. But I don't know. It's probably too soon to tell. A lot of this stuff will change over time. It's probably not even worth looking at for maybe another 6 months or a year as implementations mature on this level. Okay, so the next thing we might want to do is it's all well and good to put things into our vector, but we probably also want to be able to take them out, maybe look at them, maybe examine the contents of our vector in some way that is more interesting than just directly accessing the private members or the members that would obviously be private in a real implementation. So let's kind of start there. First, let's start with providing a slightly nicer answer for how to do this kind of formatting, which is I'm going to go back here and I'm going to add a new type here. I'm going to call it spans, continuing my very creative naming. And in the same way that pointers is going to be adding a pointer to every member, spans is going to take every type and it's going to give me a span of const type. All right. And so now that I have this type, I can add a member function called spans. And so, okay, so now how do I populate all of these spans? Well, it turns out that almost every problem in this space is packs and structure bindings. So we unpack all of our pointers and return spans, and each span is going to be a span from that pointer with the size. And so having that now, this is much easier because I can just print spans of x and spans of y, which is a much nicer thing to look at. And of course, while we're at it, might as well add an indexing operator that returns back a t, which looks basically the same way, right? We get all of our pointers and we return a t, indexing each pointer at the right index. But when we do that, and I want to look at, let's say, what v of 0 is, you'll find that this doesn't work. And so why doesn't this work? Well, our type isn't formatable, right? It's a pretty long compiler. It's not the clearest thing in the world. Because the error is not square isn't formatable. The error is you get a call to implicitly delete a default constructor of formatter square char, and you kind of have to know what it means. And so we can go ahead and add a manual formatter for square, but I don't want to do that, right? I don't like writing boilerplate code, and I don't want to have to do that. And I don't know how many of you people have implemented Rust. I'd obviously what I really want to do is just slap derived debug in front of this type and have that just work. Unfortunately, that's not an option for me for a lot of reasons. But it turns out that one of the things we can do in reflection that I'm very excited about is we can do something pretty similar. All right. So I'm gonna I'm going to implement kind of a library facility that is going to look very close to the Rust spelling of it, just purely for the sake of looking at things. There's no actual particular reason to spell it this way, but we're going to do that anyway. So one of the new things in C++26 is we have these things called annotations. Annotations look a lot like attributes, except they're preceded with an equal sign, but are otherwise an arbitrary C++ expression. Unlike Rust attributes, for those of you familiar, a Rust attribute isn't actually parsed in any way. So any Rust macro that takes attributes has to parse the arbitrary sequence of things that it gets into it. In C++, it's just a value that you get directly. There are trade-offs to both designs, but in C++ we just get the value. So we'll go all the way up here. And so in order to implement derive debug, we need a type derive with a value. Feel like I need to get a new keyboard. Oops. Right. So these things have no meaning. They're just like empty types. They're just there to make the syntax work. And now my error about things is going to go away. Okay, so I have this annotation on my type. And so what I want to do is I want to add a specialization of formatter that is going to look for that annotation. And if that annotation is present, I'll call this has annotation T of derived debug. If that annotation is present, I'm going to provide an implementation that is going to do the default thing. It's going to go through and it's just going to print all of my members for me one at a time. Now, has annotation is not a function that we have in the standard library. It's one that we tried to add, but we ended up paring down the annotation aspect of the library a lot to be really more bare bones. But it's very easy to implement, so it's not like that big a deal. And I'm just gonna show a very simple implementation of it. Just gonna look like this. So it has annotation, our reflection, which can represent anything because you can put annotations on classes, namespaces, non-static data members. You can add them on a whole variety of things. So this is a pretty general function, and it's going to be looking for this particular value. And so there's two ways to think about checking if a class has this annotation. I can look for annotations with this type and compare them, extract the value out of it as a t and compare them with equal equal. But that requires a user-defined equality comparison, which first of all means that I have to write it. And as I mentioned before, I'm lazy and I don't want to. And the other thing is that it's going to be writing user-defined code, and it'd be nice to avoid that also for performance reasons. So instead of comparing them as t's, I'm going to compare them as reflections. So I'll do this again. So should meta reflect constant of value is going to be the target that I'm looking for. And then now this is a totally normal for loop. So should number for every annotation in annotations of R, if constant of A equals target, turn true, turn false. Okay, so an annotation as a reflection has a bunch of properties. One of the properties that it has is a constant. That is like, you can think of it as like, this is the actual value of the annotation that I'm looking for. So this pulls out a reflection representing the value that the annotation is holding on to, and it's comparing it to our target. And if they match, this is true. Now, in the standard library, there's a slightly more direct API for this, but it's not actually implemented in Clang, so I'm just not gonna we're just gonna pretend that it doesn't exist. But this is fine, especially for today's purposes. So you see now that I actually have a slightly different error. Now it's complaining that I haven't actually implemented any of the functions. So let's go ahead and do this. So parse, in order to implement a formatter, we need two functions. We need parse and we need format. I'm going to fly through this kind of quickly because it's already 2:10 and this is not a formatting talk, it's a reflection talk. So I'll try to mention kind of like what's actually interesting about this and what's not. Or context.begin, because we're not going to support any specifiers. The interesting one here is format. So we're going to do two things. So we're going to start by format to out. We're going to start by printing the name of the type with an open brace. And there's a function for that called display string of t. And eventually we're going to print close brace and we're going to try out. Okay, so at this point, this should compile and this should give us just square open brace, close brace, assuming we did it correctly. Cool. So obviously, I don't think anyone's going to be particularly happy with this output because there's other values here. So the next thing that we need to do, of course, is we need to loop over all of our non-static data members. This is going to be another expansion statement where I need all the members as constant, which thankfully I've already wrapped NSDM, so I don't have to write all the define static array non-static data members thing. And for every member, I'm just going to print the member, sorry, stood format to context set out. And the way I'm going to do it is going to be similar to the designated initialization syntax. So dot name equals value. We have the name and we have the value. Okay, except of course I put this before NSDM's up. I need to put it after. And at this point, build. Okay, so now it works, right? So I get output. It's not very good output because you can see that I forgot to print a comma. So let's just do that real quick. First was true. We'll just remember to print our delimiter. This is somehow the most complicated part of formatting, even though it's the most boring, is making sure we actually like print it in a user-defined way. Remember all my semicolons. Okay, so so now we have a comma now it's separated. But know that like this isn't actually the right formatting, right? You see when I'm putting my spans, these things are nicely quoted. But this E over here isn't. Now, again, I'm gonna kind of compare us to Rust. Like Rust has this nice facility where if you just provide a question mark as your format specifier, you get nice debug formatting for everything. But we have a very incomplete solution to debug formatting right now because not all types support question marks. Certainly not all user-defined types do. Um, and so our kind of sort of haphazard way of doing this is we can check to see if our formatter supports this other function called set debug format, which I'm just going to check inline. This is not the best way of doing this, but it'll get the job done for now. But what we're going to do is we're going to check to see if the formatter for this underlying type. So I'm instantiating the formatter with the type of the member. So this is a splice of a type. Um, those need to be preceded with type name. This is okay because mem here is a constant. Remember, I declared a context for it. So I'm going to check to see if this formatter supports set debug format, which I need to make sure I spell correctly. If it does, I'm going to use the question mark, and if it doesn't, I'm not. This whole thing is a constant expression, which is fine because that's what we need. And so now this kind of gets the job done. So now I get this nice formatter. Um, so that's cool. And importantly, like if this is all library code, right? So if you think about it from the perspective of what does the user have to write, the user wrote this. Um, and that's all the user had to write in order to get SOA vector. Notice there's no macros, no any other kind of shenanigans. And I get this nice printing. Of course, this printing isn't specific to SOA vector. I could just print a square directly. Um, so that's pretty cool. But of course, this is kind of constant accessing. So the next thing I might want to do is do mutating accessing, right? Like, so what if I want to write v of 0 equals square and change it from, let's say, E4 to F4, just for simplicity. So now, kind of due to kind of the annoying circumstances of the way that C++ language rules work, this will actually compile and do nothing. I kind of wish that it didn't compile at all. It's actually possible that this emits a warning, but of course I have warnings disabled for now. So this we want this to actually do something. And in order for this to work at all, this indexing has to return basically a proxy reference. There's different ways to implement this. And so, when all you have is a defined aggregate shaped hammer, then the solution to every problem is a defined aggregate shaped nail. And so of course we're going to do it that way. But if you think about it, in order for this proxy reference to work, what we need to do is I'm going to kind of write this in code for now in a comment. So what we need is some kind of proxy type and to have references into the right X and Y members. But I also need it to be convertible to square. And I also need an assignment operator from square that's going to do something. And so this requires me to do two things, right? Not only do I need to generate members, but I also need to generate member functions. But as I said at the beginning, we can't generate member functions. The only things we can generate are non-static data members. So the way for me to do this is I can have one type that directly has these members, and then another type that inherits from it that actually has the member functions. That's kind of the only way that we can do that. So that's kind of the way that we're going to do it. So we're going to add struct proxy base. Proxy base is going to look a lot like pointers, except instead of pointers, it's going to be L value references. All right, so you can see right now it's actually complaining that I'm trying to define this thing twice. So that's fine. So let's talk about proxy. So proxy is going to inherit from proxy base. And we're going to add those two operators that I talked about. We're going to add a conversion operator, and we're going to add an assignment operator. And both of these, just like the index operator that showed earlier and a bunch of other things, are surprisingly not complicated. So one of the interesting rules around structured bindings is that they don't necessarily actually work the way that people expect them to. And I find that the way that people think that structured bindings work is that you get a binding for every sub-object of your type. So in this case, proxy, right, has one sub-object, which is a proxy base. And so you might think that, okay, well, we don't have nested structured bindings, and what I actually want to do is write something like this. But that's of course not supported. We can't do that. And so you might then think that the way to get my references is that I have to cast myself down to the base, right? Um, and this will of course work, but it turns out that the rules for structured bindings are that if all of your members are members of the same base class, those are the bindings that you get. And so this directly actually is the right thing here. Like this will give me all the bindings from proxy base. It's kind of it's an interesting choice, and I'm not really sure why it works this way, but it happens to be it happens to be useful in this context. Um, And so, of course, once I get the references, I can just construct a T out of them. Um, Maybe in some future version of C++, we can come up with a language feature to do this directly, but for now, that's just the way it works. And with assignment, we kind of do have the same shape. So we have our references, and then we have our members. And obviously, you know that this is correct by construction since all the columns line up so neatly. And in this case, I won't bother with any of the other options. I'll just do the direct fold over comma to do all the direct assignment. And so now that we have this, I can add a mutable index operator. Whoops, sorry. And it's going to return a proxy. And its implementation is going to look exactly the same way, except instead of returning a T, I'm going to return a proxy here. And now I'm going to comment out this line for now, just to see if our assignment actually worked. Okay, so you can see that the assignment worked. Actually, instead of F4, I'm going to change it to like F3, make sure that both members actually changed. And once I pivot, right, so you can see that the first element did change, that mutation did work. But now we have this issue where, okay, like my type isn't printable again. All right, because now view0 isn't a square, it's a proxy. And so we want that to work too. And so we can do this. We can add derived debug the same way. But so far, my implementation of the formatter only prints non-static data members. So that's not very good. So let's actually go back and add support for printing base classes. So I don't have a dedicated thing here, so I need to do that define static array dance again for the same way to get my bases of with T unchecked. Remember to print the limiter. Here, unlike non-static members, bases don't have names. So this one we can just format directly. Now here, I'm going to point out another Clang limitation right now, which is that, excuse me, so the way that this should work is I should be able to just splice the base class subobject like this, right? So in the same way that I'm splicing the non-static data member in this loop down here, C++26 rules allow me to splice a representation of the base class in here. But Clang doesn't implement that. So we can work around that by just directly casting ourselves down to that base using the same kind of trick I showed earlier. So one of the things that a base has is its type. We cast down to base like this. Once I do that, it's going to complain that my base class isn't formatable. And so that same annotation that I added to proxy, I also have to add to proxy base in the same way. Okay, and so one of the kind of very interesting things about this is that one of the things that's surprisingly hard to do in C++ up until now is that if I have these private nested types of class templates, how do I actually opt them in to various different library facilities, right? The way to make a type formatable is you implement std formatter, right? You provide a specialization of std formatter, but I cannot externally provide a specialization of std formatter for SOA of T proxy base, right? I can't write that. That's a non-deduced context. That's something that I cannot do. And so annotations actually allow me to work around that. Or not even work around that, just provide a solution that's much more satisfactory um, to do this, right? Okay, so now on the plus side, okay, I have formatting in prints. On the minus side, no one on Earth wants this this as the formatting, right? No one like if I'm the user using Square and using SY Square, like I don't know what proxy is. I don't know what proxy base is. I don't care about these types. This is completely meaningless to me in every way. Um, what I wanted to print is a square. So how do I do that? Like I want the formatting here to be a lot nicer. And it turns out that like I can actually do that in not a lot of code. So kind of in the same way that when all you have is define aggregate, you kind of make it work for every problem. When all you have are annotations, you can make that work for any problem as well. So we're going to add a new annotation type. We'll call it format as, which is going to just take a target type. Um, and we're going to write a new function that we're going to call, let's say, derive format type. Okay, const eval. Oh my God. Derive format. Sure. Okay. Okay, so what this function is going to do is, given a type, it's going to tell us what type we're going to format it as. Now, there's different ways to solve this problem. The way I'm going to show is probably not even a good way. It's not a very efficient way. There's definitely better solutions. But again, I'm just trying to demonstrate how to do different things. So kind of keep that in mind. And similarly to the previous example, we're going to loop over all the annotations of our type. And then if we find one whose type is format as, we're going to extract it as a format as. So now this expression has type format as, and it will not fail. It will fail if it's the wrong type, but we already checked that, so that's fine. And we're going to pull out the kind of member type in there. If we don't find one, we'll just return type directly. Okay, so one of the interesting things to point out that you might not be thinking of right now is one of the problems with writing template code is you have to be very careful about guarding template instantiations, right? Because you might have code that you're not even evaluating yet, but its existence, it has to be parsed. That parsing might lead to template instantiations. Those template instantiations might be broken and lead to compile errors. So you have to be very careful about guarding things with things like if const expr or other approaches like that. In this case, we're not instantiating anything kind of novel. So we're just worried about hitting evaluation. And so in this case, a regular for loop and a regular if are totally fine. This makes a lot of reflection code actually a lot easier to write, even if it takes a little bit to kind of get your head into like what the new domain looks like. All right. So derive format type is going to give us the type that we want to format as. So I'm going to take this and I'm going to rename this to be derive formatter, or kind of debug formatter, actually debug form, call this debug formatter. Okay, and what I'm going to do is the way I'm going to do this is that the actual std formatter t specialization, which is going to have that constraint that I had earlier, I'm going to derive from so what I call this debug formatter, derive from some specialization of debug formatter. Oh, and in particular, the one I'm going to do is I'm going to call this function derive format type of t. Okay, so by default, this is just going to be t. This is just a really fancy and expensive way of spelling t. But now I can do here, and I can go back to my proxy. I'm going to add a new annotation that is format as t. And what's going to happen now is that when I go and try to format a proxy, it's going to find that I have this annotation. So std formatter of proxy is going to inherit from debug formatter of square, right? Debug formatter of square takes a square. And so I'm passing a formatter, or sorry, I'm passing a proxy into it. So on the way into that call, we're going to invoke this conversion function that I added for no particular reason. And so what I get out is that square. And so now I have the formatting that I want. And so what do we have here? We have a structural array vector. We can support pushback. We can print things. We have this nice API to get the pieces direct separately if that's what we wanted. We can do index-based mutation and we can format it. And the user-facing API of this is nothing, right? This is actually the part of reflection that makes me the most excited is the ability to provide all of these really nice facilities to users that we just couldn't do before. Right? You have this. I think this is like a really nice API. And so in the long term, as implementations become more mature, these things are going to improve, and I think the compile times of all these things are also going to continue to improve, such that I certainly expect all of this to be dramatically better than any kind of template metaprogramming alternative, especially because one of the big advantages of the monotype design, as I've hopefully tried to demonstrate, is that everything is a function, right? We don't have to write templates anymore. And so a lot of the kind of implementation details are much easier to deal with. So yeah, I think that's probably a good stopping point of hopefully demonstrate a lot of interesting things for you all to think about. Does anyone I don't have any questions so far? Yeah, Ben?
Thanks for the presentation. So this isn't like directly about this example that you showed today, but I'm just wondering, like in the future, as reflection capabilities mature, I'm wondering if you see it as desirable for as a desirable goal to move logic like out of build systems and into like quote unquote pure C++ code.
Yeah, so that depends, right? So like I think a lot of people have use cases for code generation, examination, reflection things. And a lot of those things right now, of course, like we don't have these facilities in the language yet. So they're tooling based, code generation based. And there's there's certainly like advantages in, of course, like if you already have code generation things that you're doing in your build system, it's probably going to be beneficial to keep it there, right? Because like anytime you change anything, that just adds potential for breaking things. But there's obviously a lot of advantages in having all of your code in the same environment. Of course, like one of the challenging things with code generation tools is that if you want your code generation to understand actually what's going on in the language and you write it externally, like it can't, right? So those things are kind of harder to deal with. Um, Right now, we as I mentioned, the only code generation facility we actually have is define aggregate. So that's still kind of limited. I'm hoping we're going to have better solutions in the future. And I think eventually, yeah, that will cause more people to want to move stuff to be more in C++ proper. Not just because for the sake of just writing things with C++ reflection just for the sake of it, but because there are going to be like actual benefits for doing so. And I also know from experience that like a lot of the stuff is very desirable, so people have various different workarounds for trying to get this to work. A lot of the stuff that I've shown so far, you can actually approximate decently well using Boost PFR or techniques like that. But those techniques are extremely complicated and they're very compile time intensive. And if you compare that to kind of the implementation that I've shown here, um, I think the stuff that I've shown, like a lot of this is new. A lot of you might not have seen any of this kind of stuff before, but I think I would argue and hopefully agree that like I don't think any of this is all that complicated. It's new, but it's not complicated. So if you look at the kind of the formatter example here, like it reads very close to the actual logic that I want to write. Like, what do I want to write? Like, I want to print the name, and then I want to loop over the bases, and I want to print the bases, and I want to loop over the members, and I want to print the members. And it's kind of nice that the resulting code actually looks like that. Like it's loops. And so I'm hoping that as we continue to add facilities we make the story for wanting to use them better as we add more functionality. So I don't know. We'll see, right? We'll see. I don't know. Yeah, Jim.
Hi, thanks. Okay, so let's say that even though you're a C++ developer who thought you understood the language and even fiddled a little bit around with MPL and you thought you understood template programming, but you walk into this talk and you feel like you've missed like three or four prerequisite courses. Where would you send a person like that to kind of catch up on? Because you come right out of the gate, and hats off to you. Everything you're putting in here on in real time is compiling and that is super cool and amazing. But at the same time, like I feel like right out of the gate, I need like a couple of backgrounders between, my much less experience in this realm and then, understanding what you're doing. So if there's a reading list or something like that, it'd be great.
Yeah, so I wish I had a good answer to that. I've had people ask me that a bunch of times recently, and I don't know yet. It's true. So like a lot of this is new, and we're kind of in a different world where like the economics of book writing aren't quite what they used to be, right? Like so like on my shelf behind me, I have like this row of C++ books that when I was coming up, like I read like Scott Myers and Herb and all of them are these great resources, and I don't know what the answer to that is for modern day programming as much anymore. The C++ conferences have certainly taken off, and a lot of them do cater to like, okay, well, like, what does constant evaluation look like? What are like, how does any of this work? What are the rules around it? What do you have to think about? I'm sure there are good talks there. I unfortunately don't have like a good list in front of me. Obviously, like I've been working on this a lot over the last few years, so like it is easier for me than I expect for a lot of people. Um, on the flip side, one of the points I do want to make too is that some of the stuff here is complicated, and reasoning about how to actually construct the problem to solve in a reflection domain is a very different kind of problem than a lot of other C++ problems. But it permits the kind of libraries that we couldn't write before. And so while I don't expect a lot of people to actually write reflection code, I expect that the amount of people that will use libraries that are implemented with reflection to be approximately everybody. Um, One of the examples that I've used a lot is command line argument parsing. And so I'll kind of really quickly bring up because I'm not going to try to kind of implement it right now. Where's kind of the annotations paper? Is like if so for anyone that is implemented stuff in Rust, like the way that you do command line argument parsing in Rust is there's a library called CLAP, which stands for command line argument parser. And it's like super ergonomic and user friendly. Like you just like write something that looks a lot like this, except Rust code, obviously. And so as a user, I don't really have to understand how any of this works uh, to use the library, right? And so I kind of expect to see a proliferation of that too. And so even if some of this stuff is hard and there's a learning curve, especially around like the constant evaluation rules, it's you're going to get value out of it even indirectly. I hope. Ziha? I don't hear you if you're talking. Okay, so Jim.
Yeah, I just wanted to mention it's a really good point. Maybe analogous to, in the early days, when you're, self-teaching and, you learn about the container classes. So you think, okay, let me teach myself the container classes. And the first thing that the docs show you is the super templated container header. And you're like, what on earth is going on? And you're throwing up your hands, but then you stop and you tell yourself, okay, there's a lot of complexity here, but really the goal is to make your code simple. And so, you talk yourself off the ledge and start using them, and it's much cooler. So I appreciate that perspective, but I'm still on the ledge with some of this stuff. So any help anybody has that way, excuse me, would love to, see it in the Discord or whatever. So that's all. Thanks.
Yeah. No, I mean, I totally get it, right? And that's a good example too, right? That you can think of it as so like implementing std tuple is pretty hard. Uh, it's a complicated thing to figure. It's actually a lot easier in C++26 all of a sudden. But if you try to do it before reflection, it's pretty hard. But using std tuple is pretty easy, right? And so this is kind of the same kind of thing, I think. Yeah, Vishal?
Yeah, just was wondering, right now everything that is available for doing the reflection is only available on Godbolt. Do you know if there's any kind of hint or wording when they'll actually push both the I mean, I know that GCC has the reflection in trunk, but do you know if they'll do any sort of push for reflection in Clang or in MFVC?
So right, so G reflections in GCC trunk, and so that's going to be released as part of 16.0 or whatever, 16.1. So that's going to be April or May, I think, is when they usually do their release. So that's coming up pretty soon. Clang, so the Bloomberg fork, the P2996 fork exists, so you can use it. Although it's not maintained anymore, and Dan Katz doesn't work at Bloomberg anymore either. Uh, so you can use that, but the Clang folks are having regular meetings and talking about planning and how to do some of this stuff. And some of these features are partially implemented in Clang already. Like I know they're making progress on things like expansion statements, and some of this other stuff is only exists in this fork because it's on Clang base. So packs and structure bindings and pack indexing, those are on Clang trunk as well. Microsoft, I have no idea, honestly. I don't know what the status there is, but I never use that compiler, so it's not something I keep up to date on. But hopefully soon. One of the big things with Clang is that it seems kind of silly, like okay, but like there already is an implementation in Clang. Why don't the Clang folks just like adopt it wholesale? And part of that was kind of what I mentioned earlier. So Dan Katz implemented this, but he's not a compiler guy. In fact, this is the first thing he ever implemented in a compiler, which sounds completely insane when I say it, and it still makes no sense to me. But that's the way it is. He just decided one day that he's going to implement reflection in Clang and did it. So that's kind of how it goes. And so some of his implementation is really good, but some of it is just not the way that they want to maintain it. Especially because Clang is a little unique in compilers and that a lot of tooling is based on it, right? So a lot of stuff that people use stuff like Clang Tidy, Clang D, like other kind of tools like that, and those all still need to work. And so there's discussions on like, well, how do you manage, especially all the code generation stuff? Looking forward with that, so they want to make sure that they do a good job. And right, like I don't think people are going to be very happy if Clang supports reflection or claims to, but none of the tools work. Um, so we'll see. I know people have been joking for a long time that like, okay, cool, we ship reflection, so I can finally use it in 2040. But it's going to be available much sooner than that. And of course, one of the nice things about reflection is because it is purely a compile time construct, right? There's no runtime reflection. None of these things lead to cogen. It's purely a front end thing. None of the back end stuff has to worry about it. And so for me personally, I think it's very likely that I'm going to have reflection code in production at work earlier than we start using modules in production, which we haven't really tried to do yet, because I don't think they're ready. Which is a little unfair because modules is a much larger, more expansive language feature in a lot of ways than reflection, but also modules is C++20, and it's already 2026, so I don't know. We'll see.
All right, Barry, thank you very much for all this. Really appreciate you taking the time for us today. Just as a reminder to folks, next week we'll be back to the regular times, 11 o'clock Central.